Welcome to the Symposium of Compound Flooding. And I want to appreciate all the attendees who are listening to us. So if there is any audio visual issue, please let me know. I'm going to actually. So the general plan for today is we will start off with a general introductions, and I will present some overview points on the compound flooding. And from there, we will have each of the panelists present their work. And we will be having a chance to ask questions for each of the panelists' work. But that will be only focused on each of the panelists' research, and then we'll have a chance to have a panel discussion where we will take questions from the audience. And so the audience can interact with in two ways. One is through the webinar chat, so you could actually enter your questions there. And there's also another option where you can actually enter the Q&A icon, so you can actually enter through that way. So I'm Timothy Randhir. I'm a professor at University of Massachusetts. I also direct the Massachusetts Water Resource Research Center. And I want to introduce our esteemed panel, Dr. Hamid Muftakhari. He's an associate professor at the Department of Civil, Construction, and Environmental Engineering, also an associate director of the Center for Complex Hydrosystems Research at the University of Alabama. Has a lot of work in compound floods. You'll be listening to some of his work very soon. Next is our Dr. Antonia Sebastian, is an assistant professor with the Department of Earth, Marine, and Environmental Sciences, with a joint appointment with Environment, Ecology, and Energy Program. Also a adjunct appointment with Environmental Science and Engineering, and also directs the Sustainable Triangle field site at University of North Carolina. And our last panelist is Dr. Muthukumar Narayanasamy. Is the director of the Coastal and Compound Flood Risk at the Water Institute. He's an expert in coastal and ocean engineering, specializing in computational modeling in a variety of extreme weather settings. So with that, I wanted to actually move on into giving my overview. So my overview is essentially aimed at giving a fundamental concepts related to compound flooding. It'll actually give, for those who are not initiated, some sort of basic information about what are we talking about when we say compound flooding, but it also has some observations from recent work here and there, but that is only introductory. So I will start off with my presentations right now. So as I was saying, the threat of compound flooding is really important in terms of understanding the complexities, but also it is becoming a really important area which needs more research and work. Again, I'm a professor at the University of Massachusetts. This is sponsored by the Water Resource Research Center, which is part of the University of Massachusetts, and also funded by the U.S. Geological Survey. Compound flooding is primarily associated with when we have two or more independent or interdependent events which coincide either in space or time. These can be drivers from storm surges, high tides, heavy rainfall, or elevated river flows, or coastal tidal influences. And sometimes these can be very extensive and long-lasting, and sometimes the compound floods can be impactful than a single driver events. Um, Coastal transitional zones are pretty much highly vulnerable in those conditions. So on the right is a compound flooding probability estimates through modeling in the northern Europe, in the Europe area. Um, when we look at the compound floods, a common and devastating type is when we have the surges combined with heavy rainfall occurring. And so here is an example. One of the examples is 27 Hurricane Harvey, when we had storm surge and also with record rainfalls. Um, and the mechanism is often of interest in terms of managing these types of risk. Um, Either in terms of impeding drainage or heavy rainfall, adding to some of the coastal floods. And one additional driver is the climate change is actually going to increase the risk, especially in wet storms. When we see some of the assessments, the river flooding and coastal high tides, we see the coastal high tides often exacerbate the river floodings, and often the high tides can restrict river outflows, leading to water level increases and as well as upstream flooding. Deltas and coastal regions are highly vulnerable, and adding to the potential expectation of rising sea levels and climate change. So here is the right-hand side is some assessment on how individual effects and the joint occurrence are estimated in one of the studies by Henry. Groundwater is a huge hydrologically plays a huge role, especially when we have floodings which are sequential, which can actually increase the potential impacts as we have sequential surges. So the succession of those storms are often associated with a much more complex conditions which occur before the onset, and then also the when we have a saturated soils or even overland drainages, a single storm event can actually become devastating. So so many of the drivers of this compound floodings can be can be listed, a variety of conditions. It could be tropical cyclones or atmospheric rivers, which bring in intense rainfall in a prolonged way, monsoons or low pressure systems, or even temperature influencing some of the snowmelt conditions. So here is a coastal and fluvial wave assessments modeling in Ireland. So key components will be, usually we look for is some sort of a river discharges which are high amount of variation in tidal fluxes, storm surges which are abnormal, and also the interaction between elevated sea level rises and backwater effects. And as we see the sea level rise can actually change the baseline conditions for coastal flooding. So here is one assessment on combining some of the storm surges with precipitation in throughout the coastal regions of US and this essentially gives some sort of a evaluation of how much is the vulnerability in terms of combined influences of both storm surge and precipitation. Here are some significant flood events which occurred both in North America and Europe, and also in Asia. And this can actually change as we get into the future, when the joint return periods can change depending upon what the future entails. So here is a number of articles which represent some sort of a research which being done, which is increasing over time. This essentially reflects the amount of interest in studying compound floods and also trying to find some of the solutions. So in terms of how we are approaching this is usually some of the prediction using models, numerical models or statistical models which with cupulas, machine learning or early warning systems, And there are also approaches like management and mitigation in development of early warning systems, infrastructural improvements, which are much more resilient to these types of events. And finally, some of the nature-based solutions. So here is some sort of predictive models in one of the haiku city in China. And want to just finally summarize on what we are trying to achieve here is in terms of um, evaluating some of the resilience strategies is through advancement of modeling techniques and also studying what are the new drivers emerging through climate change, the integration of socioeconomic factors and into some sort of risk and vulnerability assessments, and how these escalating hazards can be a matter of continued update of our predictive models and capabilities. So with that, I want to end my presentation and I will hand it over to Dr. Hamid Moktafri for his talk. Hamid, I'm going to actually stop my screen.
Yes, thank you so much, Dr. Randhir. Good morning, everyone. Thanks for the nice introduction. Yeah, we already have a very nice intro to the topic. And so right now, my presentation, I'm going to mainly focus on challenges that we are having in terms of dealing with managing compound coastal floods and uh, touching upon a few already existing opportunities developed in our group, but I know that my fellow panelists are going to give you much more detailed opportunities ahead of us that we could use to manage these type of compound coastal extremes. Okay, so last September, Hurricane Helene made landfall over Florida and left behind more than 230 casualties and like more than $200 billion of damage. And if you look at the forcings, around like 10 feet of storm surge almost co-occurred with like huge amount of rain dumped over Florida Panhandle, which together is a classic example of compound extremes, as Dr. Randall mentioned in his presentation. Just a few weeks later, Hurricane Milton hit the west coast of Florida again, and again brought up almost 6 feet of storm surge and a huge amount of rainfall dumping over Tampa area. So we see that not only the temporal co-occurrence, but also the sequence of events that hitting the same region. Those are all, again, classic examples of what we call them compound extremes. If you look at the list of the most expensive weather and climate disasters in the United States since the 1980s, probably you see what I'm seeing here is too, right? A rise in the cost associated with these type of events, which are, again, the classic example of compound extremes. And there could be a number of reasons associated with that. It's not just one versus another. But if you look into the details and see why we are losing too much to these type of compound extremes, one could be probably okay in a warming climate. We're dealing with more extreme events. Like this is one a quick example that I'm bringing from one of the recent publications that we had in our group. We were showing that when oceans warm up, basically they are the source of fuel for those tropical cyclones that they supercharge. And so if you look at the so-called rapid intensification of tropical cyclones, which are basically a rapid, they increase in the intensity in a very short period of time, we found a very statistically significant correlation between the so-called marine heat wave, which is an extended period of heat, elevated sea surface temperature, and it directly links with the tropical cyclone intensity. And we showed, based on the analysis of track of landfall TCs, we showed that there is a statistically significant relationship. And if you look at the path of Hurricane Helene and Milton that I just mentioned at the beginning of this presentation, they actually went through those hot spots in the Gulf that made it like supercharged. And we end up in our conclusion, the rapid intensification is on average 50% more likely during marine heat wave, which basically happened multiple times last year. and it's not unlikely to experience in the coming years as the sea surface temperature is on a rise. So please feel free to scan this QR code to jump into the paper. But is that all? Is that just storms are getting stronger, or there could be some other components that we need to consider here? This is an image from Hurricane Harvey back in 2017, and I'm taking a snapshot of a report the National Academy published after this event, analyzing along with other events. Uh, they basically concluded that approximately half of the homes in Houston affected by flooding from Hurricane Harvey were outside the map floodplains. That could be probably another issue that we need to address altogether as a community, that we are dealing with compound floods. Whether if do we really comprehensively consider the dynamics of compound flooding at the coast, and do we systematically consider in our analysis risk assessment and planning and resilience planning? So these are three examples of the typical guidelines and manuals that are referred for frequency analysis of floods, like NOAA Atlas 14 for precipitation, FEMA documents for coastal, and USGS documents for river flow frequency analysis. Uh, uh, and probably if you look at these documents in depth, the two major challenges pop up, which one of them is multivariability of compound extremes are not systematically embedded in these guidelines and documents. Second is non-stationarity. We are dealing with the ever-changing dynamics of these events, but most of those frequency analysis are designed to be under stationary the state. And so if you look at the like a detailed discussion of what we had about how policy documents and guidelines play short in addressing these two specific challenges in compound extremes and compound flooding, please refer to this paper that we published last year. And to better highlight these challenges, I'm bringing up a few more examples to your attention. So this is a paper that we published like 2 years ago. You all might be familiar with the Saffir-Simpson scale, which we categorize the hurricanes based on wind speed. But if you look at the damage associated with these tropical cyclones and hurricanes, we mostly use to floods, not to wind effect, but we categorize the hurricanes into based on their wind speed. And that could lead in mischaracterization and miscommunication to the communities. In this paper, we basically explored how including rainfall and surge into one index that we named the multi-hazard index could help better characterize these tropical cyclones, not just based on wind, but also other factors that are involved. I do not get into the technical details, but basically, like if you look at this graph, like down here, all these events could be characterized by hurricane category 2 or 3 based on wind speed. But when you bring the effect of rainfall and storm surge into effect, you will see it's much more impactful than a category 2 of tropical cyclone. And another example is that we are having a project that through which we are engaging stakeholders in Mobile Bay, Alabama area. And we asked them, okay, what would be the scenarios of interest to you in terms of compound flooding? One very evident scenario for them was 25-year precipitation and a 25-year storm surge. They thought that it's going to be very likely compound flood that they're going to experience. And what we did to our calculations, we found that in this specific system, a 20-year accompanied by a 20-year storm surge is going to lead you into effect of like a close to 100-year event. And when we got back to them, it was quite eye-opening to them that while you're dealing with each of these drivers in isolation, you may not necessarily have a clear understanding of what would be the level of impact, because the nonlinear interaction between these drivers is going to lead into a level of impact not expected from each in isolation, or even linearly adding them up, because the interactions are nonlinear. And another example that I'm going to bring up to your attention is that when we talk about non-stationarity, we mean like typical analysis of extremes are based on a stationary assumption that do not let the parameters to vary over time. In this work, we showed not only, for example, we say okay, sea level rise gives rise to the downstream boundary condition or ocean coastal water level. But what happens is that in many cases, under variations of climate, you're going to experience a strengthened correlation between variables. So not only each of those individual drivers are going to get stronger probably, the interaction between them is going to be influenced by those climate variabilities as well. And this is another example that we show that if you consider oceanic ONI index under various climate condition versus a stationary, you will see that you for a single event, you're going to get totally different return period estimates if you let the variables of your distribution to change. So very quickly, again, my presentation was mainly focused on the challenges, but very quickly on the opportunities ahead of us. We are working with some colleagues on a chapter in a manual of practice to be published by ASCE on compound flood modeling, which I give you a heads up. Please look out for that document. There's going to be a lot of useful content in that. But one specific chapter of this manual, with our colleagues, we try to look into how can we go beyond the classic categorization of methodologies, either data-driven compound hazard analysis or process-based modeling. Can we let them link and collaborate to make a more comprehensive picture of this entire realm? And so we have some good discussions in that chapter. One relatively new aspect of it is that we are dealing these days with so-called hybrid models that try to leverage the skills from two sides of data-driven and process-based modeling. But there are different ways of combining them and making hybrid models. These are there are a lot of discussions for you that you could probably benefit. So it's going to come out soon. But I'm here to wrap my presentation up. I'm bringing to your attention two specific examples that we consider, I would consider relevant to the theme of this workshop today, which is about improving resilience. So basically, flood risk assessment, even post-flood assessment and for recovery phase, it's becoming a challenge because you either need to have local information, or you need to rely on remotely sensed data, which might not be necessarily too accurate, or numerical simulations based on process-based models like hydrodynamics models, which at the regional scale is not computationally friendly. So in this paper, we proposed merging data fusion, deep learning with numerical modeling. So, and the idea here is that let's train your algorithm locally, and then it would be much more efficient and much more accurate than simply applying those algorithms regionally. And so if you like to look at the details, again, this is going to be very helpful for recovery process, and it's quick and efficient estimated of the flood damage over regional scale, larger scales. And the last example here is that we know that there are a lot of uncertainties here and there in our simulations, especially when you're dealing with numerical modeling. And we know that satellites and all forms of remote sensing provide on near real time some data that we could. There's a category called data assimilation, that category of methods that help you update your parameters and the state variables in your model. This is another example that we thought it's going to be helpful a lot for forecasting. And so warning systems. And so to provide reliable and accurate information to those end users much more accurately and much more efficiently. I will stop here, and I will hand it to the next speaker, and we'll be happy to take questions afterward.
Thank you, Dr. Moftakari. If any of the audience have immediate questions you want to clarify, please feel free to raise your hand so that I can direct you, or you can put your question on the chat box. All right, there are no hands raised, so we'll move to our next panelist, Dr. Antonia Sebastian. Antonia, if you want to start it up.
Great, and let's see if they advance if I click. Does that go forward for everybody? Okay.
Yes.
Hi, good morning, I guess still. My name is Antonia Sebastian, and I'm an assistant professor at the University of North Carolina at Chapel Hill. And today I just wanted to provide a brief overview about the ways that I think about flood hazards research specifically as it pertains to compound flooding, and I'll provide a short example of some of the work going on in my lab. But just as an introduction to myself, I'm in what was a geology department, so it's always important to sort of quantify what timescales you work on. I'm really interested in trying to understand how floods are evolving over time, and I work on human or policy related timescales. So I look in the recent past back to maybe as early as the 1900s and to what is the distant future in terms of policy out to 2100. So typically we design on 20 to 50 year time horizons. So 2100 is really the distant future in the context of research. And I ask questions like, how did past development and mitigation decisions get us to where we are today? What types of decisions are being made in the short term, for example, after a disaster that might influence long-term outcomes? And what does the future hold, or what opportunities are there to adapt? And I find these questions particularly interesting in the context of compound flooding because compound floods impact these coastal areas where much of the world's population lives. And when those are urban, those are really dense areas that can be impacted by a lot of rapidly changing things. My lab uses everything from data analysis to computational high performance computing to answer questions like this. And if you take nothing else away from what I am about to say, fundamentally, I believe that understanding where hazards have occurred and will occur in the future is essential to our ability to prepare for and mitigate against future flood loss. So there's mounting evidence that we're getting let's say hazard assessment wrong across the board. Repetitive flooding is happening much more often than we realize. This is some work by a student in my lab that showed that between 1996 and 2020, over 90,000 buildings flooded in eastern North Carolina. 20,000 of them had flooded more than once over that time period, and about 43% of them were outside of mapped regulatory floodplains. So those are the areas that we identify as hazardous. Flood damages are also happening with increasing frequency outside of hazardous areas. Hamed also said something about this, but nationwide, about a third of all damages and a third of all insurance claims have occurred outside the floodplain since 1968. And in certain areas, these numbers are even higher. So in some work that we did in Houston, in some watersheds, you're finding upwards of 75 or 80% of damages are occurring outside the floodplain. And again, these are the areas we designate as high hazard. And then finally, the rate of risky development is exceeding the rate of adaptation, particularly in coastal areas. Some work that we did in North Carolina suggested that for every one structure that we bought out, or removed from the floodplain, more than 10 structures have been built in the floodplain, and particularly residential structures. And I would argue that we're getting it even more wrong in coastal areas. So those are sort of statistics when you look across larger scales, but in coastal areas, we are seeing very frequent flooding. So in some North Carolina communities, some of my colleagues have deployed sensors and they're monitoring water on roadways, and they have seen water on the road more than a third of the days in 2024. So up to 100 days or more in some of these communities, some level of flooding is occurring. In coastal areas, we see the rate of flooding outside of these floodplains rising much more rapidly than in inland counties. And finally, we see rapid development in coastal areas globally at rates that exceed inland areas. And so if we want to talk about safe and resilient communities, we really need a paradigm shift in how we're doing flood hazard assessment, because clearly we're not demarcating the most at-risk areas, and we are allowing for increasing populations and stuff to be put in harm's way. So current approaches to flood hazard assessment are deterministic. So we kind of assume 100-year rainfall produces 100-year flood will produce 100-year risk. They're single driver. So the flood hazard maps that we have, at least in the continental US, are either for river processes or for coastal processes, and they don't mix. They tend to be conducted at a reach or at a community scale. So for North Carolina, as an example, there are over 5,000 individual models used to assess flood hazards. And finally, they're stationary. So we don't look forward or backward when we're assessing these risks. And on average, because of just the expense and the time investment to map flooding, a flood map is recreated every 10 to 15 years, and processes are changing much faster than that. So I would argue that future approaches should be probabilistic. They should consider multiple drivers of flooding. They should be conducted at the impact scale, and they should consider non-stationarity. And so I just wanted to provide one example of work that's going on in my lab where we've been trying to take on that sort of like future approach to assess flooding from tropical cyclone related hazards. So inherently this is compound flooding, and we've leveraged a large scale hydrodynamic model called Sphinx that's developed by Deltaris that allows you to simulate processes at fairly large scales with very little computational expense, and then downscale the results to the local level. So just as a statement, I think Mutu is going to cover this model as well, but it is this opportunity to do things at much larger scales with much less computation. And so we've been using this model that we developed for Eastern North Carolina and South Carolina. We've been asking questions like, what's the spatial extent of compound flooding? What are the relative drivers of flooding across this region? How are interactions between compound flood mechanisms changing as a function of anthropogenic processes like tropical cyclone climatology changes in the wake of climate change, or development processes that are happening across this region? And what does this mean for the future of flood risk in these areas? Where do compound floods matter, and to whom? And how are they changing? And I just want to note that while the work, and this work is all led by a graduate student who just finished, her name's Dr. Lauren Grimley. And I also want to note that while we only considered tropical cyclones in this study, which are about half of the storms that have created damages over the recent period, flooding, and especially compound flooding, can be driven by storms that aren't tropical cyclones. So everyday rainfall events coupled with high winds or a high tidal event can also generate compound flooding, and we didn't consider those in this study. But so our goal was really to map what the current hazards are and what they could be in the future. And we asked this question, how will changing storm climatology influence future flood hazards? And the way that we did this was that we used a large suite of synthetic events created from reanalysis data and from climate models to simulate probabilistic flood hazards in the past and in the future. So it's a little over 1,000 tracks in both scenarios. And then we looked at the difference in the predicted flood hazard and saw, of course, as one would expect, that due to climate change, we see a lot more flooding and a lot deeper flooding. I do want to note we also did this using high resolution weather models, which are much more computationally expensive, and those are published in another paper. And one of the cool things about the Sphinx model is that we can actually attribute the different flooding to, well, we can attribute flooding to the different drivers and the different processes that are occurring. And so this allows us to actually try to tackle that question of what is being driven by compound flooding versus what's being driven by, let's say, rainfall and runoff processes versus storm surge processes. And so we can toggle things on and off in this model and isolate those different processes and their contribution to flooding. And this picture here on the left, everything that's in the darker colors are those areas associated with compound flooding versus the lighter areas, which are driven by either runoff or coastal processes. And we did this for our whole set of synthetic events in the historic climate and in the future climate. And we also looked at what's exposed to those different processes. And what's interesting is that while we see that on average, runoff processes dominate the total flood extent in these areas, compound processes are actually really important for what's exposed or who's exposed to flooding. So compound processes contribute to a fairly significant portion of building exposure, both in the present, but especially in the future. So relative to other processes, the buildings that are exposed to compound are much, much greater in the future. And so we're seeing kind of an increase of about 8% of total exposure to compound flooding in the present, moving towards 36% of exposure in the future. And I would suggest that this has a lot to do with where we're placing things now versus how processes are going to change in the future due to climate change. These results don't take into consideration sea level rise. We did a quick sensitivity analysis using a subset of these storms. So I can't say anything about how that sea level rise contributes to the relative exposure, but I will say that what we're seeing is that sea level rise is pushing the area associated with compound flooding further inland. In fact, some areas that will be compound flooded in the future are as far as 100 kilometers inland, which is that zone where about 40% of the world's population live. I'll highlight, we're talking about this for one region in the world. That doesn't mean the compound flooding will move that far inland everywhere around the world, because local topography matters. So just to sort of bring it home, I think if we really want to move toward resilience towards these more like complex types of hazards and all the interconnected risks that come from flooding, we can't adapt or mitigate to anything that we don't already foresee or can't predict where it might flood now or in the future. And so I would argue that we need better quantification of hazards using probabilistic approaches. We need to understand what's exposed now, what might be exposed in the future, so that we can make better decisions about where we're putting things today, and how we develop in these really flood-prone regions. So specifically, I would think about things like stricter development standards. I'm not suggesting that we don't develop in flood-prone regions, but we do need to think about what it is that we're placing there and how it's built. And then finally, when it comes to engineering design, obviously we should be thinking about multiple hazards. I think we often design things to mitigate a single hazard. And if we start to think about assessing cost effectiveness of a mitigation strategy to multiple hazards, we might find that some of the things we're investing in aren't necessarily the right things to be investing in right now. And then we need to consider climate change. So how are these hazards changing? What impact are this can have on things like coastal community connectivity, and where does it make sense to invest in infrastructure versus retreat from the coast? So that is my spiel. I'm happy to pass it on and answer questions now or later.
There are some, thank you, Dr. Sebastian. There are some specific questions. Graham Williams, are you able to see the Q&A icon? I can read it for you.
Oh wait, I do see them here.
So you said an understanding of historical and frequency of flooding has been the most important to your research. Are there any specific tools which have been supportive of this perspective in modeling? Were you involved in the development of,
the work that we've done in North Carolina to look at historical and the frequency of flooding leverages observations of flood loss. So that's really been a data-driven project. We've used data on flood insurance claims and policies to understand where it has and hasn't flooded in the past. And then on an event-by-event basis, we do out-of-sample prediction to develop flood extent maps for past floods. So for 78 floods since 1996. I think that's a really cool way to leverage data to fill in model gaps. So that's maybe to answer that question. The other, and then of course, so that's a data-driven approach, but we also use these simulation-based approaches to try to recreate historical floods and also generate, let's say, storylines of future floods using either historical floods scaled to the future or modeled with weather models, or to model synthetic storms that could happen in the future. I was not personally developed directly with Sphinx. I have been one of the early adopters and users, so I log a lot of questions with the developers, but no, I did not develop Sphinx, but we are increasingly one of the users of the model.
I'm going to allow Jordan, who has raised the hand, to ask the question. Jordan? Are you able to, can you ask your question, Jordan Russo? So why don't we, so why don't we pass that one for now, and please feel free to ask the question later on during the panel discussion. I just want to move on to our next panelist at this stage. So our next panelist is Dr. Muthukumar Narayanasamy. If you want, Muthu, if you want to take it away.
Yeah, it's just interesting that the three of us developed our presentations in a vacuum, and it just ended up dovetailing beautifully. So just really amusing for me. But good morning and good afternoon, everyone, to wherever you are. Thank you, Timothy, for this opportunity to talk a little bit about our activities here at the Institute. So I'm going to be talking a little bit about giving a flavor of what is ongoing. As Timothy mentioned, I'm the Director of Coastal and Compound Flood Risk at the Institute, and we have a bunch of different activities in the Gulf of Mexico and Mid-Atlantic coasts with a focus on probabilistic hazard quantification and real-time forecasting for compound flooding. So I just wanted to give you an overview of the multiple activities. So just a little bit about the Institute. We're organized into about 5 departments: coastal and compound flood risk. We have a vibrant planning and policy team. We have deltaic systems and applied geosciences and coastal ecology. Foundationally, we also have a products team that supports all the departments. We're based out of Baton Rouge in Louisiana, and then we just focus on applied research solutions to enhance community resilience. So I think Timothy already touched on this. Basically, we're defining this as an interaction between precipitation and coastal influences. In terms of the work we're doing now, holistically, we're doing compound flood modeling work in Texas as part of the General Land Office's flood studies, the river basin flood studies. Additionally, we are engaged as part of the Louisiana Watershed Initiative in developing a coast-wide compound flood model. I'll dig a little bit deeper into that effort. It involved an initial pilot in the Amite River Basin, followed by an ongoing activity to expand it to cover the entire coastal Louisiana. In Florida, in the city of Jacksonville, we're doing multiple activities founded on compound flood modeling. It's used for hazard quantification for current and future flood hazards, looking at sea level rise and precipitation changes in the future. Additionally, we're using the model for some real-time forecasting initiatives as well. So I tried to condense it into this graphic here in terms of the things we're interested in. So this box here, basically, we're trying to produce this compound flood model and data for various activities that are below it, right? So these can involve anything from near-term forecasting, nowcasting decisions and consequence modeling, to developing sustainable and resilient building codes and land use planning, using regional and local compound flood models for project-specific evaluations to ensure that the investments you're doing now protect you for current conditions as well as future conditions. One of the other, there are multiple applications, right? We can also look at watershed management policy, and also if developed appropriately, the probabilistic framework can be applied towards developing regulatory and non-regulatory products that can, again, really, it's a multi-use case depending on how the probabilistic framework is set up. To develop the compound flood model and data, what we're doing is, as Antonia mentioned, it's important to go towards a probabilistic characterization of the hazard that takes in the uncertainties and historical events. And so we achieve that by leveraging historical data on precipitation, storm surge, and antecedent conditions with an efficient and effective flood modeling ecosystem. Again, it doesn't necessarily have to be one tool. We use Sphinx. In some cases, we use HEC-RAS 2D. We're not limited. There are multiple tools out there that can be used for this purpose. And then the most important part is, how do you assimilate, how do you develop a set of events that you want to feed through a computational model, and what is the probabilistic framework that you would use to characterize the hazards for current and future conditions. So this is sort of what we're focused on. So as mentioned before, for the Louisiana Watershed Initiative, we started with a pilot study of the Amite River Basin. And what we did there fundamentally is develop a 2D HEC-RAS model that was forced by AdCirc results for storm surge, coupled AdCirc SWAN modeling at the downstream boundary condition. The placement of the downstream boundary condition was important. This was a few years back. This was version 6.2 of HEC-RAS, I think. The latest versions of HEC-RAS have the ability to ingest wave radiation stresses, but the previous versions did not. And so we had to make sure that we're placing the downstream boundary at a location such that the wave radiation stresses impacts would be minimal. The other thing we used was a HEC-HMS model for inflows, and then we used precipitation data. And so this was the modeling tool we developed at that time to evaluate the probabilistic framework. The probabilistic framework itself, we didn't build it from scratch. This was founded on the Corps of Engineers and FEMA developed joint probability method optimal sampling that is typically used to characterize probabilistic flood risk due to tropical events. So what we did was we took that framework and then we extended it to include non-tropical events and precipitation. So the standard JPMOS methodology, it considers hurricane tracks and it doesn't and parameters, and it does not include precipitation. In this case, we expanded it to include both. For a true compound flood assessment, we expanded it to include precipitation and also look at non-tropical impacts. So I wouldn't go too much into detail into this because this would turn into an hour-long talk. So with the probabilistic framework setup, this is sort of the workflow we came up with. We had about model suitability. We chose HEC-RAS 2D at that time for its ability to incorporate precipitation, flow, and downstream surge. And then we went through a rigorous calibration validation process. We ran our production runs on the Pittsburgh Supercomputing Center, and then we used the probabilistic framework to define flood hazards for current conditions. So this is sort of the workflow we used. The rainfall fields, we used the AORC data set, and then ocean weather's best reanalysis wind data. The foundational synthetic storm set we used consisted of about 645 events that were already optimized for coastal surge using the JPMOS approach. And then these were fed through coupled AdCirc SWAN, HEC-HMS, and HEC-RAS. For the HEC-RAS model itself, we leveraged a model developed by the New Orleans District of the Corps of Engineers, and then we optimized it to ensure suitable run times because we realized that we needed about more than 300,000 runs. We initially started out looking at stage 4 data for the Amite River Basin and then noticed that there was a lot of data gaps in it. Subsequently, we looked at the AORC data because it had better coverage, and also as part of the process, we realized that at least for the HMS model, the AORC data performed better against observations when compared to stage 4 data. When we looked at the RAS model itself, there was just a marginal improvement on AORC compared to stage 4, but because of the improvements in the HMS model and the fact that we have consistent data coverage, we decided to use the AORC data set for that purpose. And then we went through sort of a standard process for epistemic uncertainty quantifications using observational data. And the model performed reasonably well. Just a QQ plot showing performance against observed data for a variety of tropical events. And so we were pretty comfortable with model performance. And then when we moved into production, I mentioned that we started with a base set of 645 synthetic hurricane events. We considered about 5 different soil moisture conditions. We had a single base flow condition prescribed, and then we had about 100 rainfall patterns per storm. And this gave us about 322,000 TCs. And then for historical non-TCs, we ended up with about 1,100 simulations. So we went through production and then we developed probabilistic hazard curves. And then the first thing we did was, hey, how does this exposure for flooded structures compare when we look at compound flooding events versus just the coastal only consideration. So what we're seeing here, sort of the blue rectangles are from a coastal only effort. There's the 2023 Louisiana Coastal Master Plan. And then the green boxes are from the extended JPMOS, which is a full compound flooding effort. And we can immediately see that there was a significant impact in terms of the number of flooded structures that were exposed. Again, as Antonia mentioned, this is not going to be same in every geography, but this just shows you the importance of incorporating compounding impacts into hazard assessments. So what are we doing currently? As I mentioned, we've expanded and incorporated a fully developed and validated HEC-RAS 6.6 2D model for all of coastal Louisiana. And we could run 300,000 storms for the Emmett River Basin, but given that now we're going to be assessing the entire coastline, we're optimizing that set down based on runoff to see if we can get away with a smaller storm set for the TCs. We have developed a consistent approach to characterize base flow conditions for all the simulations. And then most importantly, the last bullet is so what, right? And that goes to the boxes at the bottom of the compound flood model that we're looking at what are the use cases for this data? How do we communicate this to communities and engineers and planners on how this data is useful? Switching over to Jacksonville, in Jacksonville, we're doing a 2-year effort. Similar, we got 5 broad tasks. We're developing 2 compound flood models. I'll explain why shortly. And then we're using the same probabilistic framework we deployed in Louisiana to look at hazards now and in the future. So we're looking at current conditions, and we're looking at 2 different sea level rise conditions and 2 different precipitation conditions. We're also looking at consequence modeling, and then we're also applying, developing a real-time flood forecasting system. So in terms of the numerical modeling for Jacksonville, again, we're using both HEC-RAS 2D and Sphinx. The idea is that for the 2D HEC-RAS model, we're using it towards probabilistic hazard characterization for current and future conditions. The Sphinx model has 2 purposes. One is to inform the development of the 2D HEC-RAS model in terms of identifying flooding hotspots, and also use it towards the real-time flood decision support system, because Sphinx is really significantly faster to execute than RAS-2D. Again, we're looking at pretty much the entire computational domain encompasses Duval County for both domains. And then for the Sphinx model, we set up about a 100-meter computational grid with a 3-meter subgrid. And this worked really well. We were able to run this in our in-house cluster in about 25 minutes for a 5-day event, which was which was helpful for our purposes. Again, and it performed well for Irma. We looked at comparisons with both gauge data and high watermark data, and we were pretty pleased with how it performed. And then what we proceeded to do was we wanted to look at flooding hotspots in the city. So we took 20 historical events from 2008, which was about 7 TCs and 13 non-TCs. And then we used Princeton developed downscaling modeling for us for precipitation for a variety of future conditions. And we analyzed that data, and we picked 2 different precipitation changes and 2 different sea level rise changes. And then we came up with a set of 100, with the idea being that we would want to know what the flood patterns are in the city. So we did that, and then we came up with this sort of a flooding heat map for the city from the 100 runs, and this really helped us understand which areas of the city were vulnerable to compound flooding impacts, and also make sure that the HEC-RAS model development considered these regions as we went towards probabilistic hazard characterization. Finally, the other application for the Sphinx model was sort of develop a real-time decision support system. So this system basically takes near real-time metocean updates, puts it into our compound flood model, which is Sphinx in this case, and then provides a variety of impact dashboards. Flood extents, flood depths, ability to navigate roadways, search and rescue grids, sorts of multiple things. We went through a whole community city engagement process to identify their needs. Also looking at structures impacted during and after an event. And this really is helping the city managers make good decisions ahead of an event. So again, to end my talk, basically, this is what we're looking at. We're trying to develop and deploy these rapid physics-based modeling and probabilistic hazard frameworks for multiple purposes. Again, we're not doing this in a vacuum. We're thankful for support from multiple Corps of Engineers districts, FEMA, State of Louisiana, Jacksonville, and then multiple academic partners and private industry folks. So it's a collaborative team. It's fun work. It's challenging work. I'm excited to be partnering with a bunch of folks to doing this. So thanks for your time.
Thank you, Dr. Narayanaswamy. At this time, if you have any questions to Dr. Narayanaswamy, you can enter it in the chat box or raise your hand so that you can interact. All right, we will proceed into the panel discussions. So I would like you to actually enter your questions or comments to the webinar chat so that we can interact. So anyway, the questions can be directed to any one of us, or it could be in general. So there is one question. You all can see the questions, right, on the chat box. So did you encounter limitations with the reduced complexity structure of Sphinx in certain topographies or urbanized settings? If so, how were they addressed? So this could be a question for anyone, who want to.
I can take a stab at it. The biggest issue that we have had is that actually, I would say this is not an issue particularly with Sphinx. This is an issue across the board with hydrodynamic modeling. The biggest issue we have faced is a lack of information on river bathymetry. So river bathymetry data is, for the models that exist, is stored model by model, reach by reach nationwide. Again, I mentioned in North Carolina, there's like 5,000 individual models where they've actually gone out, measured river bathymetry, built a model on it, et cetera. So there's no national data set of river bathymetry that is easy to access and publicly available. And so with Sphinx, what we have seen is that in areas where we lack good channel bathymetry data, we tend to over-predict water levels. So what we've done in parts of North Carolina is that we've gone HEC-RAS model by HEC-RAS model and pulled bathymetry out, burned it into our DEM in order to improve model performance. In South Carolina, we didn't have access to all of those HEC-RAS models. They weren't publicly available or easy to get access to. And so in South Carolina, our model isn't performing as well as in North Carolina. So I would say that's the #1 limitation that we have run into, but that would be a limitation with setting up any hydrodynamic model in these areas. I don't know if I can think of other topographies where we've run into issues, but that's the #1 thing we've been frustrated about, and it's more of a data limitation than it is a model limitation. Mutu, I don't know if you have other thoughts on that question.
Yeah, thanks, Antonia. I think we have tested it in Louisiana and Jacksonville. So we have not had issues there. And again, outside of the fact data availability and bathymetry, the model performance has been pretty reasonable, but I do anticipate, given the way it's structured, if for example, you go into areas with steep slopes, right? If you go further up the Atlantic Ocean, there might be issues with the fundamental structure of Sphinx, the governing equations and the modifications and how it's implemented. Also, the second thing would be there's still its application in sort of urban areas is not fully understood, where you could have stormwater and groundwater impacts. Like, how are you going to incorporate that into your model? That's another issue. And then also, if you're doing true compound flooding, how are you going to incorporate wave impacts meaningfully, right? And also, right now, I think the recommendation is for you to place the offshore boundary condition at the 2-meter water depth. But if then how does that, and also how do you incorporate wave impacts at the boundary and within the domain? So I think those can be challenges, but it's performing reasonably well in Louisiana and Jacksonville. So
And maybe I'll also just add real quickly that we ran our Sphinx model is built so that the inland boundary condition is reservoir releases, but there are no reservoirs explicitly modeled in the model. So we just put, observed boundary conditions in or simulated boundary conditions in at those reservoir locations rather than trying to put the reservoirs into the model itself.
God.
And not about the Sphinx. I'm adding up to what like Sebastian mentioned about topography issues. I'm actually part of a group. It's called Coastal Coupling Community of Practice. I thought that this might be an interest of other folks on this call. That and that committee, which is a combination of federal representatives and academia, there is a specific committee on that, like bathymetric correction. So I mean, just started how can better address it, specifically with the specific needs of coastal coupling community, which I hope that you will be informed. So if you hear of something like that receive an email, that's a comedy already going on down there. But just giving a heads up to
Actually,
people.
to add to what Hamid is saying, the coastal community of practice is a really nice thing going on. The ASCE also has a couple there's a hydrologic sciences committee that within the Coast, Oceans, Ports and Rivers Institute, COPRI. So there are a couple of really great resources on compound flooding at, let's say, organizational levels across the US, whether that's Army Corps or Association of Civil Engineers that are being organized.
Thank you. Just seeing, if there are any other questions if the participants have. So one question for the whole panel. You had been involved in a lot of complex modeling. What are some of your recommendations will be for those who are on the forefront of some of these issues of compound flooding on the ground, on what they could do in terms of actual strategies to mitigate future and as well as emerging events which are resulting from compound events. So what are some of the strategies you can recommend?
I can take a stab at it. Before I was the institute, I was in private industry for a while, and one of the challenges we faced was something simple. A lot of bridge design projects in coastal environments, right? If you look at design guidance, and I think Hamid and Antonia touched on it, the guidance does not look for compounding impacts. It's either based on flow or surge, depending on where you are. As a practitioner, sometimes, whether it's for design and planning, these sort of large probabilistic studies might be time and cost prohibitive. And so you could do something simple like, it's local, right? Compound flooding is very local. You could do scenario analysis as opposed to a large probabilistic framework. Like, what happens if I combine a 25-year surge with a 25-year rain? At least assess the impact, right? How serious is the issue as you go into planning and design? That's relatively more straightforward to do as a first step before you embark on a large initiative, right? So that would be one of my recommendations, that definitely do a due diligence as part of a design and planning process to make sure that you're accounting for these appropriately in a straightforward way. It doesn't have to be a fully robust analysis every time.
Yeah, some of my colleagues here at UNC and NC State have been working with coastal communities to try to do exactly what Nuchu's talking about, simulating sort of what if scenarios with a set of storms, or some storms that are fresh in people's minds, and looking at like what opportunities there might be to mitigate the flooding. I would say in these super coastal areas, one of the big things is backwater flow protection. So sea level rise is a real problem. When it comes up via the storm sewer network, then you get water on the roads that wouldn't normally be there. And so there's some like really small opportunities to mitigate what I would consider one of the things that looks like compound flooding. But I think what's been really interesting and what they're finding, and this is Catherine and Artie and Hino's work, what they have been seeing is that there are adaptation strategies that might work in the very short term, and might mitigate flooding in the short term, but like breakwaters or whatever. But as climate change happens, as sea level rise happens, as storm climatology changes, those solutions might potentially exacerbate compound flooding in the future, right? So you could imagine that something that blocks sea level rise or blocks waves today could actually enhance inland flooding as storms get more severe, like rainfall increases due to climate change in the future. And so then suddenly you actually are creating a bowl and holding water. And I think the Netherlands is the example of this, like on steroids, right? So by trying to mitigate one hazard, you're actually exacerbating another hazard. And that all to me is within the scope of compound flooding. And so I think that that's really important, the scenario building, to try to look at like these investments that we're making now in the very, very short term, how are they going to play out in the future, and what kind of unforeseen maladaptation might be happening because of them. So that would just be something I would point out in that context.
And already great points already raised. I have two specific points in mind to mention. One of them is that to my understanding of the community, we need to more and more recognize the hydrologic characteristics of the systems that we are dealing with. I guess there's a lot of focus and attention to the hydrodynamic side of it, but when I'm saying hydrologic is storage capacity in the system. Like a very typical assumption is that like the storm drainage network is already overwhelmed, soil is already saturated. So those type of assumptions that have not been a traditionally part of the hydrodynamic simulation of compound floods must be better and better, as both Muto and Tony mentioned, like a number of good examples that we more and more need to recognize those different hydrologic aspects of the compound flooding, which should be implemented in terms of simulations. The other aspect, which I would basically we have just recently started to look into, is that I mentioned about mischaracterization of the risk when you focus on one specific driver. I would say the other mischaracterization that could have happening in the past and could be probably is that focusing on one specific aspect of flooding. So let's say flood is not just depth or extent, it's also velocity. But we haven't had much of those type of information. We're currently working on characterizing it based on combining various aspects of flooding and seeing whether if it's going to be more informative. Of course, that those information is not among the classic type of information being communicated to the end users. Like I know that like yeah, we have either flood maps or flood depth information, velocity, even if it's calculated using hydrodynamics models, is not being systematically communicated. Except for a specific case of erosion or wave load. So it's not common to communicate velocity in the products. But what I'm saying is that again, future looking, I'm saying is that implementing more of first other aspects of hydrodynamics, not just depth and extent, and other aspects of hydrology, more comprehensively considering hydrology in terms of storage. You talked about groundwater effect, drainage network capacity, all other forms of storage that could have happened in the system that basically contribute to more realistic representation. Then those are my two probably points here.
So that's a very good point, in terms of looking at some of the resilience capacity. I think you're talking about storage as a resilience capacity, and groundwater saturation as a resilience capacity. And then you have also vegetation and the dynamics of different resistance and of the coastline. And so, perfect. So there is one hand raised. Jordan, if you want to, I'm going to allow you to talk. I don't know if it's okay. You meant, no, it's not meant to. It was an accident. So are there any other questions? I mean, there was a questions. How do you think the concept of compound flooding is evolving? And how well do you think it's being understood by planners, policymakers, and the public?
From a terminology standpoint, I think when we first started talking about compound flooding, we were really talking about this surge plus rainfall or riverine flooding phenomena. I think the definition of compound flooding has evolved considerably to consider space and time components. So is something compound over a certain region, right? So Hamed brought up the sequential storm issue. So are two storms following each other, is that a compound event now? And also the question of over what region is something considered compound? So are two storms in the Gulf a compound event when you think about FEMA as your end user or your stakeholder? Two storms over anywhere in the US can trigger compound risks or impacts because they're trying to recover to both events simultaneously. So I think our definition of what a compound event is has expanded considerably to the point where we're also now talking about multi-hazards and other things. And I think it can get really confusing in that sense. And we've tried in this panel to like stick to sort of the coastal multiple driver definition here. But I would say that I think that the evolution of what policy makers and stakeholders understand has increased significantly. I more and more, and maybe Mutu and Hamed can also speak to this, but more and more, I think even community members are coming out and asking, you know, like obviously it's not just rain that's impacting us, it's also sea level rise. And so I do think that there is a public recognition of the issue. I would also say that resilience officers or floodplain managers are asking more and more about the issue of groundwater levels rising due to sea level rise. So I think that it is on the public's mind, but I do think it is the question around like how you model it is where the complexity comes, not so much the understanding of the phenomena or what might be driving that. But I don't know if others have other thoughts on that.
I think there's, yeah, again, going back to like what I've seen over the last decade, or at least the last 7-8 years, there's been progressive understanding and recognition of this. Like the earlier design projects, it was a struggle to communicate to people that this is important, right? Like you need to consider both. From that to, I was at a conference last year, there were 7 papers on compound flooding. Granted, one of them had a 100-year surge with a 100-year rain and a 100-year flow in a model. But at least there were initiatives on that front, right? And even from communities and cities, what we're seeing the projects we're working on, like at least at the city level and planning and policy level, people are starting to understand and recognize that it's important to characterize and quantify it for like efficient planning and design decisions. It's not going to be impactful everywhere, but people are looking at it to make sure that it's accounted for at an increasing rate.
There's another question which was earlier. How are compound models being tested in other countries? I think Antonia answered some on Mozambique application, but if you want to add to that, how applicable would they be in data scarce regions, and any workarounds that you recommend? So anything to add to that on applications elsewhere?
The one thing I will say is that one of the things we're seeing in some reanalysis stuff we're doing right now is that in areas, and this holds for more than just Sphinx, this is hydrodynamic modeling in general, but in data scarce regions, when you don't have good topography or bathymetry data for that matter, you tend to overpredict flooding on average. And so That is going to be a limitation of these models no matter what. So even if you're, relying on global remotely sensed data sets, they tend to be at, I think the best for topography is like a 90-meter resolution. So I would expect that you would mischaracterize flooding a little bit, but perhaps in the direction of being conservative, I'm not sure. So that would be my answer. I don't usually work in data scarce regions, so I'm the worst person to ask this question.
Yeah, as Tony mentioned, like there are some good examples that our European colleagues and some other US researchers have already done, trying to be global. But I that's absolutely true. So I guess one big limitation is you already referred to, like they discuss regions. Even the reanalysis products are not going to be that accurate because they are bounded by the availability of the data. And so if that becomes even worse, because when it comes to compound flooding, you need overlapping records. So you not only need record, you need overlapping wrong record. And when it comes to frequency analysis, it's like if for one variable you need like 20 to 30 years being sufficient to get your statistics right. When you're talking about multivariates involved, you need longer record, overlapping record. So I can imagine if we go, there'll be a lot of stretches of the coast globally that we don't have such information. And even relying on reanalysis is gonna give us huge uncertainty bound, because they're good at the point that they had observations to validate and calibrate the models, but where there is not, it's just an estimation. Definitely they're useful, but we need to be realistic when we're dealing with that. Just they might not be that accurate to characterize the correlation structures. The timing might not be perfect. So from forcing to topography to whatever you need for analyze compound flooding, I guess it's a big issue. So I guess getting back to the question, how useful are these? I guess theoretically they should be applicable everywhere, except if you have reliable record to do that. But to my understanding, more and more becoming like more and more remotely sensed products available, it's gonna be helpful. And so my suggestion is that do not simply relying on the forcings and the topography to simulate and say this is compound flooding. These days, more and more flood inundation maps become available through remotely sensed data from fusing multi satellites. So I would, especially for those locations, I would definitely check those products. And the other suggestion, the other direction of the community is machine learning algorithms to get trained as specific features, influential features at the point that you have sufficient data, and then explore those patterns at like on-gauge basins and locations. So like if the opportunities lays there, but have been integrated, I don't think so yet. We still have like huge uncertainty bound around those points.
Yeah, I think good points. I mean, the only thing I would say to add to that, the data scarcity is not just limited to compound models, right? Any flood model, that's a general challenge. So I think the other thing to look at, if it's data scarce, the first step would be to look at low cost sensors, right? I mean, it's never too late to start collecting data. And the second would also be, what I've noticed is even if you don't have robust historical data, relative sensitivity analysis or scenario planning using these models might be helpful to at least understand the significance of each hazard and them in combinations, right? So a couple of those strategies can help, even if we don't have sufficient data.
Have any? Yeah, I don't have any questions listed in the chat box. A quick wrap-up question, I would say. I think there is one question. So, what methods do you use to identify the most influential source of uncertainty in your flood simulations?
So I can take a stab at that. I mean, well, there's multiple, right? For epistemic uncertainty, as I showed, we use historical gauge observations and high water marks. Now we're looking at SAR-derived flood extents and flood tips, because we are, as Amit and Antonia mentioned, remote sense data. So can we use satellite data to derive flood extents for historical events and use that for uncertainty quantification? Right, so there, and then again, given the fact that compound flood models will take other model inputs, like for example, if you're using Delft 3D or AdCirc models as input, then there's uncertainty from that model that sort of leaks into your model that you can try and quantify. The wind data produced, either if it's the ECMWF or OWI winds, they have uncertainty in them. So all of these, I mean, there's ways to do it. So there are traditionally, at least in the JPMOS space, there was a process, it was just, there was no spatial variability in the bias and uncertainty originally, but now there's a shift towards quantifying bias and uncertainty spatially to account for that in the probabilistic framework.
And I left in the chat box a link to one of our recent papers, which we specifically looked into that aspect of compound flooding, how uncertainty stems from various sources, how it could be quantified, how it could be reduced through some methods. So, and I'll be definitely happy for follow-up discussions if you think any value of continuing the discussion.
Excellent. Any other questions to the panel? So one wrapping question I have is some of the satellite and remote sensing technologies, so like LiDAR and other uses, which can get into much more high resolution data observations. I'm just curious how those types of systems or remote sense technologies can be used in data scarce regions, to be prepared or actually augment whatever data we have.
Yeah, so I mean, I think a lot of these models are built on remotely sensed data sets, right? You mentioned LiDAR and other things. I would say that maybe to answer a question that wasn't asked, the data set I'm potentially most excited about is SWOT, SWOT, the Surface Water Ocean Topography Mission, which is circling the Earth every, I don't know, repeat passes like 21 days or something like that. And it measures water surface elevations. And so what's really cool about that is that while it might not pass over during a flood event, I think we're going to get a way better understanding of slopes in rivers, slopes in estuaries, when there's a flood event, the potential for what those water depths look like. So it's just this whole new data set that's going to be available for validating or at least quantifying uncertainties in those models. I think there's also going to be a lot of spin-off products from that data set. So one of the things people are talking about or working on is trying to use SWOT to back into what channel bathymetry looks like. And then we might have a global channel bathymetry data set. It's probably going to be relatively low resolution, but it's going to be better than having nothing, which is where we are now. So if you ask me what I'm most excited about in the short term, or where I think there's a huge potential that is coming online, is through the SWOT mission. So that would be my answer to the question.
Excellent. So I think we don't have questions in the chat box, and I would really like to appreciate the panelists' participation and exciting discussions about compound flooding. And I also want to thank all the attendees who participated. And so feel free to reach out to any of the panelists as well as to the Water Center if you have further questions. So with that, I wanted to really appreciate the panel and hope we could give a big hand, but it's a webinar, but thank you so much.
Thank you for the opportunity and thank you all for attending.
Yeah, thank you.
See you all. Bye-bye.